Hello everyone, my name is Marzi Hidari. I'm a PhD student at Carleton University. I worked alongside Abdullah Al-Shahabi, Hao Yan, and my supervisor Yuhan Gu on this research. I'm excited to present our work on a unified framework for heterogeneous semi-supervised learning. Semi-supervised learning, or SSL, is a fundamental task in machine learning, empowering models to extract valuable insights from datasets with limited labeled samples and a large amount of unlabeled data. Current SSL methods assume that the unlabeled and labeled data are sampled from similar or homogeneous distributions. Such an assumption presents substantial practical limitation to applying traditional SSL methods to a wide range of application domains where labeled and unlabeled data can have different distributions. For example, in the field of medical imaging, it is common for labeled MRI scans to be sourced from state-of-the-art research hospitals, while a lot of unlabeled scans could come from a series of rural clinics, each with its distinct scanning equipment. In such setting, the challenge lies in leveraging the unlabeled data given its dissimilarity with its labeled counterpart. To address the current limitation of traditional SSL, we propose a novel heterogeneous semi-supervised learning task, where the training data consists of labeled and unlabeled data sampled from different distribution domains. The two domains contain a common set of semantic classes, but have different label and class feature distribution. The goal of HSSL is to train a model using the heterogeneous training data so that it can perform well on held-out test sets sampled from both the labeled and unlabeled domains, without posing distribution similarity assumptions between the labeled and unlabeled data. HSSL is expected to be applicable to a broader range of real-world scenarios compared to a standard SSL. The novel heterogeneous semi-supervised learning task, however, is much more challenging due to the following characteristics. Number one, the domain gap, which is expressed as divergence between class feature distributions across the labeled and unlabeled domains, present a significant challenge to model generalization and learning. Number two is the absence of annotated samples from the unlabeled domain during training, which further compounds the complexity of the task. And number three, considering that the test set comprises samples from both domains, the device solution methods need to accurately model the distribution inherent to each domain. It is imperative for the models to discern not only the domain from which a sample originates, but also the specific semantic class it belongs to. In this work, we also propose a novel method named as Unified Framework for Heterogeneous Semi-Supervised Learning, or UNI-HSSL, to address the HSSL problem. The proposed method learns a fine-grained classification model cohesively under a unified framework by combining the labeled and unlabeled class categories within an extended and precisely doubled label space. The framework consists of three technical components designed to tackle the HSSL challenges: a weighted moving average pseudo-labeling component for stable label updates, a cross-domain prototype alignment component for semantic consistency, and a progressive inter-domain mix-up component for domain bridging. We have a 2C class classification model comprised of feature encoder F and probabilistic classifier H that will be trained by leveraging both the labeled set and the unlabeled set within a pseudo-labeling based SSL framework. On the labeled set, the standard supervised cross-entropy loss will be used as a train objective, where the concatenated label vector expands the ground truth label vector into the 2C class label space by appending a zero vector with length c to it. Although we have obtained initial pseudo-labels for the unlabeled set by utilizing the pre-trained C-class classifier, those initial labels are unavoidably noisy due to the existence of domain gap between the labeled and unlabeled domains. In order to effectively leverage the unlabeled data, we update the pseudo-label for each unlabeled instance during each training iteration in a weighted moving average fashion. This weighted moving average update strategy can yield a smooth and adaptive assignment of pseudolabels by promptly incorporating the progress in the classification model and mitigating the risk of oscillatory updates. Moreover, to further mitigate the adverse impact of noisy pseudolabels, we deploy a cross-entropy loss on the unlabeled set during training, selectively utilizing only instances with more reliable pseudolabels. Given that the labeled domain and unlabeled domain are comprised of the same set of C semantic classes, there is a one-to-one correspondence relationship between each cross-domain class pair for the same semantic concept. In order to facilitate knowledge sharing and transfer across domains, we propose to align each semantic class from the labeled domain with its corresponding semantic class in the unlabeled domain within the learned feature embedding space. To this end, we present each class using a class prototype vector and design a cross-domain semantic class prototype alignment component to enforce the corresponding semantic class pairs across the domains are more similar in the feature embedding space than non-corresponding class pairs. Specifically, we compute the prototype vector for the kth class in the label set as the average feature embedding of the label instances belonging to the class. We compute the class prototype vectors in the unlabeled set based on the instances with reliable pseudolabels. Then, for each semantic class, we align the prototypes of the corresponding class pairs from the labeled and unlabeled domains by employing a cross-domain contrastive prototype alignment loss. In order to bridge the gap between the labeled domain and the unlabeled domain, we propose a progressive interdomain mix-up mechanism to augment the training set by dynamically generating synthetic instances between the labeled set and unlabeled set, with the objective of facilitating steady and efficient knowledge transfer from the labeled domain to the unlabeled domain. Specifically, we generate an interdomain synthetic instance by mixing a labeled instance from the labeled set with the pseudo-labeled instance from the unlabeled set through linear interpolation. In the standard mix-up, the mixing coefficient lambda is sampled from a fixed beta distribution with hyperparameter alpha. To facilitate a steady and smooth adaptation from the labeled domain to the unlabeled domain for HSSL, we propose to dynamically generate the mixed-up data in each training iteration T by deploying a progressive mix-up strategy that samples lambda from a shifted beta distribution based on the schedule function psi. Following the schedule, at the beginning of the training process, we have a psi of 0 approximately equals to 0.5 and lambda is sampled from the approximate interval of 0 to 0.5 as the model prioritizes the labeled domain, guarding against noisy pseudo-label predictions from unlabeled data. As the training progresses, the model gradually increases its reliance on the unlabeled data, and the interval 0 to psi of t from which lambda is sampled is expanded gradually towards the interval of 0 to 1, allowing it to adapt seamlessly between domains. Following previous works on using mix-up data, we employed the mix-up set for model training by minimizing the mean squared error. By integrating the classification loss terms unlabeled set, the unlabeled set, and the mix-up set with the class prototype alignment loss, we obtained a joint training objective for uni-HSSL model. Here, lambda PL and lambda PA and lambda mix-up are trade-off hyperparameters. We evaluate the proposed uni-HSSL framework on the heterogeneous semi-supervised learning tasks and compare it to 4 categories of baselines: supervised learning baseline, semi-supervised learning baselines, unsupervised domain adaptation baselines, and bidirectional adaptation baseline. In this table, mean classification accuracy and standard deviation within parentheses on the Office Home datasets using the ResNet 50 backbone is reported. The first domain in each row indicates the labeled domain, while the second domain indicates the unlabeled domain. We can see from the table that our UniHSL framework consistently outperforms all the baselines. Thank you very much for your attention.